Good evening and welcome to Everything Matters, Tales from the Periodic Table. I'm Ron Hipschman, and what I'm going to do now is give you a little talk about boron itself. Boron is a really interesting element. It's the number 5 over right there. Sorry, I have to use my t-shirt. I don't have a periodic table up here yet. Well, actually, yes, I do. Let's put a periodic table up there. Boron is number 5. It's the 5th element. It's right there. Here it comes. It's kind of a metal and kind of a non-metal. It's a metalloid, and it has some very interesting properties. It was discovered back in 1808 by these three guys here, Joseph Louis Gay-Lussac, Thenard, and Sir Humphrey Davy. Now, the two guys on the side, they're the ones that actually discovered the element, but they didn't actually refine it into a metal or into its pure form. Sir Humphrey Davy was the first one, about a month after it was discovered by the other two, who actually was able to make it into a pure element itself. If we look at the elements in general, we want to talk about where they come from. This is a nice periodic table. It kind of says where these things come from. So you'll notice that there are kind of different colors going on here. You'll notice that hydrogen and helium are kind of darker blue, and they came from the Big Bang. But you notice the next three, lithium, beryllium, and boron, are kind of this lightish blue color, and it says cosmic rays. That's kind of strange. Now, the Big Bang did not make lithium, beryllium, or boron. As a matter of fact, they're not made in the middle of stars like a lot of the other elements are. As a matter of fact, stars kind of consume those things if they happen to be in stars. So where do we get the boron? The boron comes from the collision of cosmic rays with other elements in the universe. So, for instance, that's called spallation. Spallation is, well, we could just demonstrate it here. Here's a carbon nucleus right here, and a cosmic ray, say a neutron, very fast neutron, comes in and it hits the nucleus and bang, it knocks a couple particles out. Well, it's no longer carbon. If it only has 5 protons in the nucleus as opposed to 6, it's not carbon anymore. It's boron. And that's how boron is made. It's actually made by the collision of cosmic rays on other elements, knocking out fragments of those other elements and leaving behind a lighter nucleus, in this case, boron 10. Now, boron comes in 2 different forms, 2 different stable forms. There's boron 10 and boron 11. Boron 10 has 10 things in the nucleus, 5 protons and 5 neutrons, and boron 11 has 11 things in the nucleus, still 5 protons and 6 neutrons. And those are the only stable forms of boron around. There are lots of unstable forms of boron, lots of isotopes they're called, but none of the isotopes of boron actually, they're all radioactive, and none of them last for more than a second. So in the universe in general, there's no boron except for these 2 right here, because they decay. If they're created, they decay almost instantly. And you can see here that boron 10 is about 20% of the boron in the universe, and boron 11 is about the remaining 80%. And that's what we find here on Earth. Boron is a bigger atom than hydrogen. I always like to do a little comparison here. So here you see kind of a comparison between boron and hydrogen. Hydrogen is one of the smaller atoms. And it has other interesting properties as well. Its density, how dense is it? It's about twice the density of water. Water has a density of about 1 gram per cubic centimeter, and boron's about twice that. And just for comparison, if you want to see some other densities, gasoline is less than water, so gasoline floats on water. We know that because we've seen these beautiful colored puddles where the gasoline's on top of the water, making those beautiful bubble-like colors. Magnesium is a little lighter than boron. Aluminum is about a little more, and so on. Iron, which makes up the core of the Earth, about 7-8 grams per cubic centimeter. Gold is a real champion there at 19 grams per cubic centimeter. And osmium is the absolute champion of all the elements at 22 grams per cubic centimeter. So, boron, kind of a middle density. How hard is boron? That's where it gets interesting. Boron's atoms are linked to each other in crystalline form very rigidly. So boron tends to be very, very hard, at least in its crystalline form. You notice that this is called Mohs scale of hardness, not because it was invented by a guy named Mo, one of the Three Stooges. No, it was actually invented by this guy whose name was Mose. Yes, and so it should have, I suppose, an apostrophe after it, but it's never done that way. Here, and he classified the hardness of minerals by trying to scratch one with the other. It's a good way of doing it. So, for instance, talc was, he did this with minerals. Talc was one of the, had a hardness of 1 because he could scratch it with gypsum, which has a hardness of 2. And these are kind of arbitrary numbers that he gave these things. But here you can see all the ones in blue are the minerals that he used in his scale. So we go from talc through gypsum through calcite, fluorite, all the way up to number 10, which is diamond. And you'll notice that boron and a compound of boron, boron nitride, is very hard. It's just below diamond, barely. Just below diamond at 9.5. So it's an extremely hard substance. It'll scratch everything except diamond. It'll scratch rubies. And the rubies are very, very hard. Because the atoms are linked together, it's got a lot of, sound travels through it very, very quickly. As a matter of fact, if you look at a table with the speed of sound, air is about 343 meters per second, about 1,000 feet per second. Remember, that's how you find out how far away lightning is. You listen to you see the lightning, you listen for the thunder, you count the number of seconds, multiply by 1,000, and that's how far away it is in feet. Well, that doesn't work as well with boron because it moves through, that lightning flash would move through boron at 16,000 meters per second. It's the biggest of all of them, actually. So sound moves through boron quite fast because those atoms are linked to each other with very strong springs, very strong bonds. So what does it look like? It has 2 allotropes. Allotropes are different forms of the same thing. For instance, graphite is an allotrope of carbon, so is diamond. Well, in this case, this brown powder is the amorphous. It's not a crystalline structure. They're kind of linked randomly to each other, the atoms, and that you get this brown powder. And the other allotrope here is this crystalline boron, and I can show that to you. Actually, this is kind of a magnified piece. Those pieces are actually in here. They're actually pretty small. Should I take them out? You can look at them? Hold on. There we go. Maybe we can get that up on the screen. Maybe not. Well, you can. There we go. There's those. Well, almost. We got them. Have them there for a second. So there's the boron. That's actually metallic crystalline. Well, semi-metallic crystalline boron. And this is just a few grams of it here. Boron's about $5 a gram if you want to go out and buy it. So it's fairly expensive. Okay. Put that away. Got to thank my buddy Ethan Currens for supplying me with the boron. Where do you get boron? Well, believe it or not, if you travel to a town called Boron, by the way, the town was named after the element, not the other way around. This is actually in California. It's the borax capital of the world. Borax is just an oxide of boron, and you mine it. And you notice that if you go to boron, you can go to either one direction, you go to the world's largest open pit borax mine, and the other direction, you go to the missile test site at Edwards Air Force Base. Great town, Boron. Go there. Here's where that open pit mine is. So it's in the Mojave Desert, very near to Edwards Air Force Base. It's just to the northeast of Edwards Air Force Base, and there you can see the open pit mine that they mine a quarter of the world's borax in right here. The other 75% is in Turkey. Here's what the mine looks like. It's actually kind of nice at sunset. How do you get it out of here? Well, nowadays, of course, you truck it out, but back in the good old days, everyone knows how they got it out, right? 20 mule team. So actually this was how they mined borax in Death Valley and also in the town of out near Boron as well. And 20 mule team, of course, became the name of many products. So 20 mule team borax. This is my favorite, I think this is my favorite product box of all time. I just want to point out that we have a kid here and it says here, have your child join the 20 mule team safety patrol. I'm protected. Caution, keep out of reach of children. And notice he's holding a box of borax with him holding a box of borax with him holding a box of borax. I think it's one of the early examples of recursive art. I also like the 20 mule team Boraxo up there for children's bath. Soothes the skin. Ah, yes. So borax looks sort of like this. The one on your left there is just crystals of pure borax, the kind of hexagonal. The one on the right here is borax, which is kind of the brown stuff, and the white cubes are salt, sodium chloride. It's called halite. And they occur together because borax is water soluble, and the only place that you get it is where it concentrates. It's not very concentrated in the Earth's crust, and so the way it concentrates is you dissolve it in water, and the water flows into a basin that has no outlet, dries up. More water flows into the basin, dries up. More water flows into the basin, dries up, and eventually you get a dried lake bed that you can mine the borax out of, and that's what we have in the Mojave Desert. So this is one form that you can get boron from. There's this borax mineral. Here's another one, kernite. Notice it has kind of a linear structure to it. Kernite, obviously, it must be in Kern County, would be my guess. And this one of my favorites, is ulexite. And ulexite, again, has a bunch of very needle-like crystals. And here they're kind of splayed out, but in this one on the left, they're all laying right next to each other. And those crystals can actually act like fiber optics. And it gives you a mineral. I have a few pieces of it here. Actually, maybe Jim can come over and look at this with the monitor. This is called TV rock. Many of you have probably seen this. Because these are, you can see on the edge here, when you look at it, I'll pass a few of them around, you can see that actually, you can probably see it with the camera here. We'll bring it up on the screen. A bunch of parallel, oh, I can't see behind, there we go. You see the parallel lines there? And that allows you to use it as a fiber optic, so anything that is on the bottom of it appears on the top. So you see the TV rock there is transmitting the image from below it. So I'll pass these out so you can just take a look at them yourself. Oops. Okay, let me pass those out. Take one over here, take one over here, and I'll start one back over here. There we go. It's kind of a cool mineral, ulexite. So that's one of the minerals that we mine boron out of. And what do we put it in? What's it used for? It's used for stuff like this. You already saw it used in the 20 mule team borax detergent booster. But it's also used in bleaches, in Fixodent for cleaning dentures, in laundry detergent, even for toothpaste to whiten your teeth. Because what happens is the borax is in a compound, sodium hyperborate. I have to remember, sodium perborate, excuse me, sodium perborate. And when you heat up sodium perborate in the washing machine or even in your mouth, you get hydrogen peroxide, and that's a really good whitener. It's a good cleaner. And so that's what's used in all of these products right here. Another place where it's used, and we're going to see more of this after I talk, is in borosilicate glass. When you add boron to various other substances, you get a glass that does not expand or contract much with temperature. The thing that breaks glass, if you shock it thermally, is say you put a glass in a hot piece of cold glass in a hot liquid, is the outside of the glass hits the liquid first and expands more than the inside of the glass, and that will cause a fracture. Well, if you have a piece of glass that doesn't expand much, then you can prevent that fracture from thermal shock much better. So it's used in Pyrex that you might have in your kitchen. Pyrex is a brand name. It was invented by the Schott glass company, SCHOTT. It's also used in labware because there you have a lot of different thermal things going on in labware. Boron is also, boron 10, not boron 11, boron 10 is a really good element to capture neutrons. Why would you want to capture a neutron? Well, if you have a nuclear reactor and you'd like to slow down the nuclear reactions in your reactor, you might want to put some boron in there, and that would slow the neutrons from causing more fissions in the core of the reactor. And so usually when they shut reactors down, they take the water, the cooling water in high pressure reactors, and they will inject boron, borax really, into the liquid, and that will stop the reaction from happening or slow it down anyway. And then when you're starting the reactor up, you slowly purify the boron out of the water and start the reactor up. So I have another thing here on the table that we use borax for, roach powder. Roach powder is really just boric acid, and I don't know why there's a straw on that one. That's suspicious to me, but anyway. Boric acid is an insecticide. It's also, boric acid is also a mild bactericide as well. So you can actually use it to mildly sterilize things. As a matter of fact, when I was a kid, I remember when I had eye infections, we used to have this little eye cup, and my mom would mix up boric acid in water, and you'd put it in your eye, open your eye with it, and it would help cure whatever you had in your eye. It doesn't seem like, yes, put this acid in your eye. It seems like the wrong thing to do, I know. But the other thing that boron does is it colors flames. I wanted to do a little demo of that for you. So what I'm going to do here is let's take some of this roach powder. I'm going to put some of it in a cup right here. By the way, boric acid is almost non-toxic. It's only mildly toxic. You can actually take quite a bit of it. I'm going to put a little bit of it in this cup right here. And what I'm going to do is I have a stainless steel wire right here, and I'm going to dip the wire into a little water here, and I'm going to get a little bit of that boric acid powder. There we go. Onto the wire here, and then I'm going to put the flame to it. Now, if you were here for lithium, do you remember what color lithium made a flame? Made it into a beautiful red flame. Let's see what boron does. Okay, the proper is ooh and ah. So the green color is from the spectrum of boron, and that's actually used, let me cool that off, there we go. It's actually used to color fireworks. You notice the second firework over and this firework over, this green color in fireworks, that's due to the additive of boron. So it's used to color fireworks. Boron can link things together. It has lots of chemical bonds, and one thing you can link together is silicone oil. When you link silicone oil with boron, you get the stuff that comes in this egg, and we all know what that is. What is it? Silly putty, yes, absolutely. So silly putty is actually a boron-linked silicone elastomer, and it's kind of interesting stuff. We all know silly putty. It is, if you stretch it really slowly, it stretches. If you stretch it quickly, what happens? It breaks. There we go. That's cool. And you used to be able to pick up newsprint with it when newsprint was oil-based. The soy-based does not pick it up, but you used to be able to pick up comics out of the paper with the silly putty off the paper, and then you could print them onto another piece of paper. It bounces, so it's elastic. It was actually invented during World War II as a possible substitute for rubber, but it didn't quite work. There we go. Bounces pretty good. Silly putty, wonderful thing. Again, because of its cross-linking capabilities. What else do we have? Oh, there's one demo. This is kind of a YouTube video that I just had to show you, but, well, coming up. There's also boron in rare earth magnets, but combine the two now. Combine rare earth magnets and silly putty. If you take and put iron inside of silly putty and make silly putty magnetic, you can then add a magnet right next to it. See what happens. Roll the video. It's like the Blob. Wasn't Paul Newman in the Blob? Yeah. And I know I'm supposed to be doing this quicker, but I just have to watch this entire thing. It just, no matter how many times I see it, I can't take my eyes off of it. This, by the way, took place over an hour or so this is a time lapse. Yeah. Oh, God, that's such a good video. Okay. So satisfying. I have to make some of that stuff one of these days. Now, the last one where the cross-linking becomes important and where you can put things together with boron is we're going to do a little demo of, and I'm sure you've all had this toy as well. It's kind of related to silly putty, except instead of putting silicone oils together, we put alcohols together. And that stuff we all know as what? Slime. Yes. And so slime is made, again, of polyvinyl alcohols linked with, there's the polyvinyl alcohols on the left and linked with boron, and they ties all of those chains of atoms together, and you get this slime, this non-Newtonian liquid. And we have with us tonight from our Explorables program, we have David Mangiante. He's going to come in. We're going to do a little cooking demo for you. Is that okay?
Yeah.
We want to cook up slime and show you how to cook up slime at home. Is your microphone on?
I don't know.
It
yes,
is, yes.
Lovely. Ron, I have a gift for you.
Oh, thank you. Can I be like that little
You
kid
can
there?
play with that.
This is slime. And David's going to show us how to do that. And I'm going to cook along next to him.
Cool.
Just like, like on Oprah or something like that. What do I do with this now?
You hold
I'm going to cook, but I have to cook and hold the microphone.
No,
how do I do that?
You can put it back in the bag.
Oh, my God.
Howdy, everybody.
By the way, I have to do your full introduction here.
Okay.
So David is a geology graduate student at UC Berkeley, so you can probably talk more about the geology that we saw there. And he's the lead volunteer for our Explorables program that designs and facilitates hands-on activities here at the Exploratorium on the weekends usually. Mm-hmm. And he has some really great things, and today he's going to show us how to do this. So
this is one of the activities that we do on the floor with kids and adults. Often, instead of me standing up here doing it, you would be doing it. You'd be doing all the things I'd be doing here, except tonight, I'm doing it. You'll have to come back another time.
Can I do it?
Oh, you can do it, Ron. Okay. So, Ron, I'm just not going to do anything. I'm just going to have you do everything.
Oh, really?
Yeah. So first thing I want you to do is we're going to give you some water. So I'm going to take the beaker here. It says water. I'm going to fill it up with water.
To that level right there?
Oh, you can fill it all the way up.
All the way up.
Yeah. Lovely. And then we're going to take our 20 mule team borax here. If you can take this and pour a little bit of that into this little beaker here, maybe up to the 20 milliliter line.
20 milliliter line.
That's great.
Okay.
And then we're going to add some more water to this. Here, you can do it.
All right, you got it. Go ahead, you do it. Okay.
So this is going to make a saturated solution of borax here. And it's actually, here, we can use one of these here. We're going to dissolve the borax in the water.
Boy, that's going to be really saturated.
Super saturated, completely saturated. And we're going to make boric acid. We're going to make, I think you showed earlier on the monitor, that boron that was binding the glue together. That's what's going to be in here. Go back to it.
There we go. Oh, so let's go one. There we go. We'll go forward one more slide. Hang on. There we go.
Yeah, so right here, this little saturated solution here is going to be that boron in the middle. So we need to have the rest of the stuff, though. What's going to be on the outside? And tonight we're going to be using glue. This is clear glue, and the clear glue is going to be on the outside, and the boron's going to be the inside. It's going to get it all held together into that slime you had.
You can use Elmer's glue, too,
You can use Elmer's glue as well. I like this glue because it's clear, and you can see colors. And you can make it fluoresce, you can make it glow in the dark as you add things to it. So go ahead and pour in, fill up this now to the same level as you fill up the water.
All right.
You're doing great.
It's viscous.
Yeah. Keep.
About the same, 50-50, huh?
Yeah. Perfect.
Right there.
All right, so we want to add color, though, because clear slime is really boring. So I'm going to let you guys choose. I have a collection of colors here. We have a pink color. We have a blue color. We have blue. Blue. Okay, she likes blue.
I was going to go for magenta.
Oh, that's
myself,
exciting. Okay,
but,
so I'm going to pick pink. You're going to pick blue. That's great. We're going to add both of them in here, a drop of each of them into our saturated solution.
do we have to decant this out?
No, it's going to be fine.
Okay.
Maybe we'll
It's
get some
chemistry.
particulates.
It's not physics. It's chemistry. So.
Well, so the amazing thing actually about slime here is that unlike many of the things that are exhibited here at the museum, this one has actual chemistry that's going to be happening. Make sure I do the blue.
Yeah, we don't do a lot of chemistry at the
Yeah.
Exploratorium. It's really hard to do chemistry in a museum because you end up with stuff that you have to get rid of after.
Right, like this. Whoa. Ooh.
Wow, the blue really is much stronger than the red, huh?
Yeah. We could add more red.
No, it's okay.
Okay.
I think the blue's kind of nice.
Lovely. All right. So now what I'm going to have you do is in this large beaker,
Yes.
in our Pyrex beaker, we're going to pour in both the glue and the water. Both of them into here.
Okay. Glue. And water. And do we stir that?
Yep.
So we're making kind of a dilute glue.
Yeah. And it's just glue, so there's nothing. It's like kind of goopy, but it's not actually slimy quite yet. All right. So
Yeah, the bubbles
now
are kind of
here
rising
comes
through
the
it.
exciting part. I'm gonna move some things out of the way. What I'm gonna have you do is I'm gonna have you stir like the Dickens here.
Okay.
You ready?
I'm ready.
Stir with this end.
Stir with this end.
Yeah, the drumstick. We're playing music here.
Wow.
So go ahead and stir. And as you stir, I'm gonna pour this in.
Okay, I'm going to put the
All
microphone
right,
down.
you can put the microphone down. I'll just talk. So slow it down. And can you feel some solid forming at all? Is it getting harder to stir it at all?
Getting more viscous.
Cool. It says it's getting more and more viscous.
Oh,
Is it getting solid? Okay. Now slow it. Now we can stop stirring it. The next part is going to be. Oh yeah, you can see it. It's already stuck on the stir. You can start pulling it out. Blah. So this was a clear liquid and another mostly clear liquid that we mixed together, and suddenly we got something that's pretty solid that came out of it. I'm going to add a little bit more borax. Now the fun part begins where you're going to stick your hands in here,
Okay.
and you're going to pull out the slime. So go stick your hands in there.
It's ready?
It's ready. And you're going to want to goop it around in your hands. You want to mix it in your hands.
I see.
It's gross.
We don't have we don't have
This is why I had you do this. I had paper towels.
we don't have
Don't
any
worry.
paper towels here, do
Oh,
we?
yeah.
Yeah, underneath, Ryan.
Oh, okay.
I
Great.
brought them special for you. I knew it was going to be gross. I hope you're not wearing rings.
I am. Make me clean after.
Yeah. All right, so you pass it to me and I can scoop it around as well. So as it gets mixed in, as the boron, the borax gets mixed in with the glue, it'll get more and more solid and it'll flow or stick together more and more. So the interesting thing about this actually is that it's sort of a solid and it's sort of a liquid. Just like the silly putty that we saw earlier, Ron was saying that it can stretch slowly, but can also break. I can break off chunks of it. And I can also bounce this, but it gets kind of messy because it's really slimy. Bounce. Who is this person in the front row making demands of me? What's going on over here? I'm not going to bounce it. You can bounce it yourself later, though. And so this substance that we made here is actually quite similar to another substance that's actually exhibited on the floor here at the museum called oobleck.
Oobleck.
Yeah, which is just cornstarch and water, and it's up on the mezzanine near the I forget where it's at. Observatory, that's the one, yeah. The difference between that and this is that we did actual chemistry to make this happen rather than just a physical interaction.
Just watering.
So this is a new chemical compound that we've made from the borax and from the glue. All right. So actually, we have a little borax or a little slime for all y'all to take home with you as well.
Who wants?
Who can get? Each person can get their own slime. You can get slime.
Get slime.
You can get slime.
Get slime.
You can get slime. Everyone can get slime. You can get slime back there. Everyone wants slime.